So, when we talk about circulation, I'll ask a question on the test. It won't be in this depth of circulation, but it'll be a kind of an excerpt of this of major parts. We go from the right atrium through the tricuspid, right ventricle, pulmonary semilunar valve, pulmonary artery, lungs, pulmonary vein, left atrium, bicuspid, left ventricle, aortic semilunar valve, aorta, arteries, arterioles, capillaries, venules, veins, back to vena cava, and we start over again. Obviously, that will be a horrifically long multiple choice question if I put this in there. So there'll be something similar to this, but it'll be much shorter. I may go right atrium through a valve to the lungs, back to the left side, and then from there, semilunar valve to the body, and then back. So I'll shorten it up, but it'll still be in sequence. This will help you ask several questions, or answer several questions, because I'll ask where blood's going from here, or where did it come from to get here. So this will help you on a lot of different things. Now the right side of the heart is what we need to concentrate on and start with, because its purpose is the pulmonary circuit. The right side of the heart's sole purpose is to get blood to the lungs. Get blood to the lungs. This is a low pressure, low resistance pathway. If we had a lot of pressure and we pumped a lot of blood into the lungs with a lot of pressure, we're going to blow out a lot of capillaries, because there's a lot of little bitty capillaries in the lungs. So low pressure, low resistance pathway. We go right atrium, tricuspid, right ventricle. The right side of the heart, just pumping to the lungs, is much smaller than the left side of the heart. It doesn't have to work as hard. It's still significant though. Pulmonary semilunar valve, pulmonary artery, lungs, pulmonary vein. There's three things there we need to look at. Pulmonary artery. Let's make this statement. This is a true statement. All arteries carry blood away from the heart, and that is true. All arteries carry blood away from the heart. If we say all arteries carry blood rich in oxygen, we would be true on everything but one, and that's the pulmonary artery. Because it's going where? To the lungs to get oxygen. So that's the exception to the rule. And of course, lungs is where gas exchange occurs. When we get to the respiratory chapter for test 5, we'll talk about diffusion. Basically sums up that entire chapter. If you had one word, it would sum it up. And then the left, or the pulmonary vein coming out of the lungs. If we say all veins return blood to the heart, that's true. All veins return blood to the heart. All veins return blood to the heart. And if I said all veins carry blood low in oxygen, that's true for all veins except this one. The pulmonary vein is the only vein that carries blood rich in oxygen. Where's it coming from? Lungs.
So all veins carry blood.
Lock yourself out. Yep. So all veins carry blood low in oxygen except the pulmonary vein, which carries blood rich in oxygen coming from the lungs. Then we make it to the left side of the heart, left atrium, bicuspid, left ventricle. The left side of the heart, as we'll see in lab this week, is much thicker than the right side of the heart, because it's pumping to the whole body. It's pumping top of your head, bottom of your feet. It's like taking 20 pounds of weights and lifting with your right arm, and 5 pounds of weights and lifting with your left arm. Which arm's going to get bigger after a while? Yep, your right arm. So we pump out of the left ventricle, the aortic semilunar valve, into the aorta. The aorta is the largest artery out there. And then arteries themselves are, if we do an artery vein comparison, arteries are thicker. They have elastic recoil. They withstand more pressure. They are considered resistance vessels. Resistance vessels. Arterioles, as we drop down to the next size, arterioles provide the most resistance to any blood flow. They can. Arterioles is what can totally shut off or can dilate and allow blood to flow in a certain direction. If you think about chapter 9, when we were shunting blood in a fight or flight, where was we taking blood away from? Digestive system, reproductive system, excretory system. We didn't need blood there during our fight or flight, did we? How did we keep it from going there? Arterioles. They just squeezed off and didn't let any blood go in that direction. It's the arterioles that allow us to focus blood where it needs to go. Most resistance. And then capillaries is where gas and nutrient exchange will occur. Very, very small. They say there's 1,250,000 capillaries per square inch of your body. That's a lot of capillaries. We can't have blood in all those capillaries at the same time, obviously. So it rotates as we need and sends it there when we need it. You'd think capillaries would provide the most resistance to blood flow, but if arterioles can totally shut down blood flow, that's as much resistance as you can get. Capillaries are always open. Although they're so small that a red blood cell has to squeeze to get through a capillary, they're still open. Now, to tell you how small they are, a red blood cell, they say, is about 8 micrometers in size. That tells me absolutely nothing because I can't even imagine a micrometer. If we look at a ruler in millimeters and centimeters, yeah, but a micrometer, we don't have anything in our hands that measures that small. But they'll tell you in the book, if you take 50 red blood cells and put them side by side, shoulder to shoulder, and line them up, they'll reach across a period at the end of a sentence in your book. So that, now we can relate to that a little bit. That's small, just squeeze through there. Now we need the red blood cells to single file squeeze through capillaries though, because the capillaries is where they're getting out into the individual tissues and dealing with individual cells. So that's why they need to be slow so they can dump oxygen and pick up the waste. See, pick up carbon dioxide. If they're zipping through there at the pressure they're in arteries, then they probably missed the bus stop somewhere. Things are not going to get on and off near as easy. So we need it to slow down. And then we dump back in the venules, veins back in the vena cava. Veins are considered capacitance vessels. We had arteries as resistance vessels, veins as capacitance vessels. The reason is, at any given time, most of your blood is found in a vein, found in your veins at any given time. We said the other day, your number one mechanism to return blood back to the heart is muscle contraction, because pressure in the veins is poor. Pressure in the arteries, 100 millimeters of mercury. Pressure in the veins, 2 millimeters of mercury. So blood's not just going to flow due to pressure. Now pressure, 2 millimeters of mercury is significant here, but muscle contraction is going to squeeze that vein. Where's all your veins found? Veins are going to be within and around muscles. So when a muscle contracts, it affects a vein somewhere. And that pushes the blood forward because all veins have one-way valves. It prevents backflow. It prevents backflow. So once blood gets to a certain level, it doesn't just turn around and drop back where it was. It keeps inching in that direction. So things as simple as breathing moves blood. You getting up, moving around, moves a lot of blood. Circulation is improved with muscle contraction. So that's a major part of the muscle physiology one. Did anybody pick that one? See, that would be significant there, and even down to the cells producing more mitochondria to produce more energy. As your body gets used to doing more exercise, it'll build more reserves for that exercise. And I think that's a big point to make on that, because a lot of people say, well, I'm too tired to exercise. Well, you're too tired not to exercise. As if you continue to lay around and not do anything, that's exactly what your body prepare you to do. And that's sad, but it's true. To get more energy, you have to make yourself produce more energy. So, there's a lot of, I'm curious to see y'all's, because I think there's just so many different things you can hit on that, and you could probably make that into an easy 30-minute presentation. So you'll have to cut and dice to keep it at 10 or 15 minutes. All right, so we're back to the vena cava. We've circulated. We know quite a bit about arteries. We know about arterioles being resistance vessels. I'll point out in here as we go the things about that. Capillaries, where gas and nutrient exchange occurs. Veins, capacitance vessels. And unlike arteries, veins are kind of like water balloons. The more you put in them, the bigger they get. And arteries, the more you put in them, they have a reflex coil that they want to snap back. And that snapback is what maintains pressure. You put more in a vein, it just keeps getting bigger. So there's your major differences in those. Now I think, let me raise that up. We'll go ahead and leave it on the floor, Tracy. I want to look. I'll make it heart big today because we have a camera on it. Well, I want to look at electrical excitation. Is that one of the things that's on there somewhere? Electricity to the heart. We mentioned systole and diastole there. Okay. So that's kind of where we're at. Electrical excitation of the heart. You have an SA node, SA, AV, AV bundle, and Purkinje fibers. There's your electrical sequence of events that must happen for your heart to beat the way it does. SA node, and I'll ask you on the test what's the proper sequence. SA stands for sinoatrial. AV, atrioventricular. Does that help? AV bundle, also known and maybe talked in your book about, they call it the bundle of His. It's spelled his, but it's pronounced hiss, like the snake on Robin Hood. Hiss. You've seen Robin Hood, right? You have children. Okay, you're on top of this lecture then, aren't you? Bundle of His, and then Purkinje fibers. This being your right atrium, left atrium here. The SA node is your pacemaker. It sets up about 70 beats a minute. And chapter 13, I think you'll see, it'll say 70 beats a minute, and 14 might say 75 beats a minute being normal, or vice versa. I don't remember which chapter says what. But if my heart's beating 70 to 75 beats a minute, I'm good. If your heart beating 40 beats a minute, we've got a problem. The good news on that is it's still beating. If your heart's not beating at all, you have a serious problem. You know what I'm saying? So that's what we're going to look at here. SA node is sending out a message at 70 beats a minute, and it tells the atria to contract at 70 beats a minute. That's what it's telling the atria. That's electrical current that goes through the atria. So both atria contract at the same time. And basically, while all they're doing is pumping blood from here to here. Now, most of the blood, probably about 80% of the blood that was in the atria, has already simply diffused into the ventricles. It's already there. The atria is going to jam in another 20%. That's all this little contraction is going to do. So the SA node sends a signal out. This electrical current does not make it to the ventricles because this muscle through here does not conduct electrical current. So about 0.2 of a second later, the SA node sends a message to the AV node. And the AV node sends a message through the AV bundle, which comes right through the septum, to the Purkinje fibers, which tell the ventricles to contract 0.2 of a second after the atria contract. So if it takes 0.8 seconds to do a complete cycle, and that's about what it takes. If you think about it, there's 60 seconds in a minute. We can do 70 beats a minute, so that's about 0.8 seconds. 0.5 of that, the heart is relaxed. It's only working 0.3 of that, which is still significant. It gets its job done. So both atria contracted at the same time. 0.2 of a second later, both ventricles contracted. Okay, now they're all relaxed. And then we start the cycle over as blood fills in. So now there's a Frank Starling law that's in your book somewhere, and as we scan this chapter probably on Wednesday, I'll find it for you. And basically what Frank Starling got his name in that book for saying is that the ventricles will pump in the amount of blood that came in them. They'll pump out the amount of blood that came in them, but there'll always be some blood left behind. They can never totally empty themselves. And with that law, comes into play a lot of physiology, because if there's more blood left behind, there's a problem somewhere. It's either leaking back in, or the heart's not strong enough to overcome the pressure that's out in the vessels. And that's where hypertension can really work a heart to death. If there's way more pressure out here, we're supposed to be pumping blood into this vessel in the vessel's relaxed state. We've got to overcome 80 millimeters of mercury in this vessel. So the heart builds to what? 120? In theory. Which should be enough to overcome that. But what if the vessel is the diastole, or the relaxed state of the vessel? What if it's sitting there at 100? Will 120 get it all in there? Probably not. So you have leftover blood in the heart. Now when that ventricle fills again, it fills with more blood than it's used to, and it has to get bigger. You ever heard of people with enlarged hearts? A lot of times they have to get bigger to deal with the capacity that they have to deal with, still not getting all the blood pumped into that vessel. So that's why it's so important that the diastole, which systole and diastole is 120 over 80, that is so important that that number right there stays down. This number, it can get up, it's about 140 to 145. They start worrying about that number. What will drive that number? This number. If you think about it, if this number goes up, we have to drive this number to overcome this number, right? We have to keep that distance. This number, anywhere around 90. And they're, from what I understand, not seen it in books yet, they're trying to lower normal blood pressure. They're wanting it about 115 over 70 is what they're trying to say is normal. I don't know how they can change that with life being the way it is. 120 over 80 has been normal forever. How do you just tell somebody you're not normal anymore and you're 120 over 80? I don't know how they can change that, but that's what they're trying to say.
How big of a difference is it between the two? The 120 over 80 and 115 over 70?
Not that much difference. Y'all may be mathematically better than I am off the top of your head. There's 40 difference here. So there's 30, 45 difference there. Yeah, so, yeah, this number is what they pull down the most. But when this number goes up 10, it's huge. This number can go up 25 before it becomes huge. So, I mean, the strength of the heart pumping is not near as hard as the amount of pressure it has to build to overcome 100 or 90, or, I mean, that's what they're looking at there. It's very short term, but it ends up being pretty significant. Now, a trained athlete, we're saying 70 to 75, a trained athlete may have a resting heart rate of 60. I've seen them with 55. Below 50 is bad, okay? But why could a trained athlete have a resting heart rate of 60? And if that's better, why?
It's their heart muscles build up.
Their muscle has been exercised to the point of strength. And in 60 beats a minute, it can pump the same amount of blood as our heart does in 70 beats a minute. And in some cycling situations, 50 or 55 beats a minute can pump the same amount of blood as 70 beats a minute. And you get below that, you get into some serious heart situations. And some cyclists actually wear heart monitors because their heart rate drops too low. And cycling is a very hard exercise, hard form of exercise. But usually below 50, they start looking to see if you even need a pacemaker because your pace is not high enough. So if we go back over here and look at this, here we have the SA node at 70 beats a minute. Then we have the AV, then we have the bundle, and then we have the fibers, or Purkinje fibers. What if the SA node decides to quit?
The AV node picks up.
The AV node picks up. Is that good?
No.
Well, you're alive.
It's
That's
better
good.
than not.
It's better than the alternative here, isn't it?
It's not good at all.
The AV node will pick up at about 50 beats a minute. That's all it knows to do on its own. And so, you know something's not right. You're not feeling good. You're kind of lethargic, but you're alive. And you're kind of conscious. And so, you go to the doctor, they get you into a cardiologist, and he puts you on a treadmill, right? We're going to do a treadmill test. But don't worry, if you have a heart attack, my surgery team's waiting just outside that door. And so they try to kill you. They try to kill you on the treadmill. They put you through a stress test. Oh, my heart's giving me a problem. Yeah, we're going to see just how much it can take. That's what we're going to do. But don't worry. We've got all kinds of electricity and we've got surgeons waiting, so we can fire you back up. So, sure enough, they put in a pacemaker. So, AV's not having to do the work. The SA node's back in action. We've got you a Duracell battery in there, and just every now and then it'll jolt you just for the heck of it. They've got those that are, I don't even know what it's called, but it's every now and then people that's got them.
The
Fibrillators that's built in.
Yeah.
And I've seen them just be walking down there, bam, and they just get hit. It's like, holy smokes, that is a pretty strong Duracell battery right there. But anyway, what if SA's back to working and the AV decides to quit? It don't want to do its job. It's like, it's not fair. I did his job and now he's back. I want some vacation here. Now what happens? See, that's our connection from atria to ventricle is the AV. So without the AV, SA's pumping the atria at 70 beats a minute. The bundle of His is going to pick up the ventricles at 30 beats a minute. So we have 70 beats a minute of blood coming in to the ventricles and 30 beats a minute of blood going out of the ventricles. That doesn't add up, does it? You know what you call that? Congestive heart failure. Yeah, you end up with a lot of congestion before that's over. And toward the end of this chapter, I believe, we talk about a first degree, second degree, and third degree node block. And that's what is happening here is an AV node block. And I believe a third degree is where nothing's coming through. A second degree, you get 1 out of 4 or 5 signals coming through. And a first degree is where 1 out of every 2 or 3 is coming through or something like that. We're still kicking with the first degree. Second degree, we're not doing well. Third degree, we're not doing well at all. We better get some help in a hurry because congestive heart failure is not gonna stabilize anything. Poor old Purkinje fibers at the mercy of everything else. They have no life of their own. That's just the way it goes sometimes. All right, where does that get us so far? Some of this stuff on this page that we're looking at here, we talked about pulmonary circulation, right? That's the right side. Systemic circulation is the left side, so we don't want to miss that. Systemic is left side. In lab today, we'll cover papillary muscles, we'll cover chordae tendineae, we just covered diastole and systole. Septal defects, we're gonna talk about the septum in lab this week. And, the septum is the muscle between the two ventricles, and sometimes there's holes in that. A septal defect would allow pressure in the left side to build, try to force it out, instead it shoots back through the hole back to the right side, and that can cause pulmonary edema, where you end up building blood back up in the lungs, and that's not a good situation. Most of those can be fixed and repaired though. Mitral stenosis, rheumatic fever, we'll pick all that up in the book. Lub dub, we'll talk about in the book. We've already talked about all valves, they prevent backflow. And electrical stimulation, we just talked about. So we'll pick up probably in the chapter on Wednesday. We'll glance through this chapter. Most of the stuff I've already talked about or something I've missed, we'll pick it up Wednesday and try to be finished with chapter 13 on Wednesday. Any questions? See you in lab tomorrow.